We're going to get started. All right, so welcome everybody to Beyond the Cript Practical iOS Reverse Engineering. My name is Michael Allen, and I am a security consultant with IOActive. Obviously, I'm interested in assessing mobile applications, but I also do penetration tests, code reviews, vulnerability assessments, and so on. Incidentally, IOActive, we are hiring, and so if you are interested in joining the pirate ship, then just hit me up outside, and I'll be more than happy to field your questions. So, why this talk? It's partially, based on my own personal experience. When I started out testing, for example, mobile applications, I couldn't care or didn't pay attention to what was happening under the hood, right? I pretty much just ran the common tools that were often recommended, got some results, and that was pretty much it. And that worked for a while. But then, at a point, I hit a snag, and so I had to change my approach. And so there might be persons who are here now who are currently at that point and would like to move beyond it, or it could be that you have been testing third-party applications, and you kind of want to move beyond that and get more into iOS, the iOS system itself. And also, the fact is that a lot of the common bugs that you would usually find using the approach that you'd normally see being recommended on blogs and so on are pretty much closed. And so, at some point you're going to have to change your approach. So, the outline. So the approach we're going to take is we're going to start out with the current state of the union, right? So we're going to look on the common tools that are currently available now, the results they produce, and it's going to bring us up to the point where we realize that, a lot of the common bugs are now closed, and so we're going to have to change our approach. And that new approach is going to involve a deeper understanding of what's happening under the hood. So we look at what a macro binary is, what a Mac task is, look at Objective-C and Swift from a reverse engineer's perspective. And then we'll wrap up with identifying, simple jailbreak detection routines and how they can be bypassed, right? So the first thing is you're going to, need to build your toolkit. And so we're going to look at the common toolkit or the, kind of general toolkit that you'd see often being recommended now. So we'll just go through this. So the first thing is, of course, you're going to need a jailbroken device. And jailbreaking, the process of jailbreaking is just removing the restrictions that have been imposed by iOS, right? You are weakening the security posture of the device because you are exploiting vulnerabilities. And so the recommendation is to have a dedicated testing device. The latest jailbreak, public jailbreak now, is Pangu 9.2 to 9.3, only supported on 64-bit devices. And there are private jailbreaks, iOS 10, for example. Lucas Tedesco just, published his. And then briefly, what's jailbreak? The types of jailbreaks. Tethered, requires a computer to start the device. Untethered, it's the opposite. And semi is a mixture of the two. So the latest Pangu jailbreak is semi-tethered, as each time the device gets restarted, you have to run the application again to re-jailbreak the device. Just some tips here. Change the default root password from Alpine. I would, also encourage you to access the device over USB instead of using Wi-Fi. And so use, USB MUX-D. You pretty much run TCP relay, specify your port. Would also recommend that you use SSH keys. Generate your keys, copy your public key over, and also add an alias for your device so that you don't have to be typing in the password every single time you want to access the device, right? Moving files. You're going to want to move, during an assessment, you're going to want to move files between your host and the device itself. Recommended tools, iPhone Box, iExplorer, but really, You don't necessarily need those tools. You're going to be accessing the device over SSH anyway, so you can always use SFTP. I've also had problems with a particular tweak for iPhoneBox. The AFC2 has given me some trouble, so you could just use SFTP. Intercepting network traffic. Most applications are going to need, well, speak to a backend server, usually over HTTPS. The de facto tool for intercepting traffic is Burp Suite. You could, of course, use ZAP or the Z-Attack proxy, but the main tool is Burp Suite, and so you have Burp running on your host machine, assigned to an IP, listing on a particular port, and then from your device, you configure your device to connect to that machine on that particular port as well, right? The problem you'll run into is that most of the applications these days use SSL pinning, which means the certificate is now in the binary itself. And so to bypass that, you use SSL kill switch. SSL kill switch, however, is no longer being maintained. And so the new thing now is SSL kill switch 2. And pretty much it's just a tweak you install and you enable and disable as required. Keep in mind that when you do enable it, you are disabling SSL certification across the entire device, which again goes back to the recommendation of having a dedicated test device. Right. So instrumentation. The usual tools you'll see again is Cript. So you basically inject into a process. You get an interactive console. The syntax is, a mixture of Objective-C and JavaScript. Only supported right now on iOS and OS X. And just recently, the folks over at Now Secure had a fork, so they replaced the runtime. So the script runtime is now powered by Frida. And incidentally, the talk is entitled Beyond the Script. No, this is not a knock against script. It's a powerful tool, but if you do in fact want to move beyond that, then the talk is just aimed at laying that foundation. So how do you use Cript? Pretty much specify the process ID that you are interested in instrumenting, and then just run script -p, provide the ID, and that's it. You're in the interactive console, where, as we said, the syntax is Objective-C and JavaScript. The new hotness, however, is Frida. This thing is pretty much on steroids, crack cocaine, heroin, you name it, right? So it allows you to inject the Google's V8 engine into the target process. And so that JavaScript now has full access to the process memory, supports function hooking, access to native methods, but more importantly, you can inject into a starting process, right? And it also supports a whole lot more architectures than does script. And so with the combination of the Frida runtime engine and the script interactive console, you now have the best of both worlds. So this is just a very simple example of using Frida. And in this example, we're just, specifying a particular application that would like to instrument, and we want to see every time a particular method is called. And so the -u is over USB, the receive is for functions that start like that, and we're just tracing each time one is called. But this is merely not even scratching the surface. Like I said, a lot of tools these days are now powered by Frida. During an assessment, there are some common tasks that you normally go through, right? And these include things like, checking the keychain, looking at logs, and, just some mundane tasks. And so there are tools that automate all of these common tasks, and some are listed here. They, however, have varying levels of support. So, for example, Snoopit is no longer supported. And so the one that's interesting is Needle. This was released just recently at Black Hat. And so the example here is shown of, IDB tool, logging, keychain dumping, provides just general app info. And pretty much looks like this, right? And then the fact is that most of your work is going to be done in the from a command line, and so you're going to need some essential tools. And so the recommendation again is usually to use Big Boss or Erica Utils. But I'd also like to recommend using the iOS bin pack, which is a number of tools that have been compiled for the iOS platform by Jonathan Levin. And some examples of the binaries that are included in that iOS bin pack are listed here. Keep in mind, and my recommendation would be, so you get a tar file that you pretty much switch over to your root directory and just untar it, and all the files get copied to where they're supposed to go. I have lost jailbreaks because of that, because some binaries didn't play well with some of the installed tweaks that I had. So if you're going to go this route, may I suggest you choose the binaries that you're interested in, copy them over to your device, rather than just using them all. I've spoken to him about this, and he has said that he has used it on several devices with no issues. So it may have been that a couple tweaks that I had installed caused an issue. So keep that in mind. All right, so that's the basic toolkit that you'd usually see. And so now we're going to get into what usually happens during an assessment, right? So again, let's go back to intercepting traffic. The application is going to communicate to a backend server. You can use Burp, or you could set up a remote virtual interface. So you plug the device in to iTunes, get the UDID, grab that ID, and then just run RVICTL-S device ID. That brings up an interface, and then you can just sniff on that interface. You can write to a PCAP file, and then you can use your network tool, your favorite network tool, to then parse that file, right? Insecure storage, most of the attacks are based on insecure storage. So property list files stores serialized objects, key value pairs. Sometimes they are in binary formats, but you can use the PLUtil tool to convert that. And in this example, this is Photo Vault storing the access pin, my super secure access pin in the plist file in plain text, right? So you have information leakage here. Client-side data stores, SQLite databases, most often are used for client-side storage. Just a lightweight client-side database, and you query using SQL. Again, you might find sensitive information being stored, and in this example, we're seeing the administrator username and password again being stored in plain text. Fun fact about SQLite. Delete doesn't actually do what you think. So when you delete data, it gets added to a free list, right? And those free records are not overwritten until more space is required. The end result of that is that the data might not be overwritten for a while, and it can therefore be recovered. Something to keep in mind. And there are, of course, tools that will allow you to recover this data. Dumping the keychain. Under the hood, it's just a SQLite database stored in var keychains. You can query it again using the SQLite 3 command tool. Of course, SQLite 3 command line tool would be in the repositories that we spoke about earlier. Or you could just use keychain dumper and dump the entire contents of the keychain itself, right? Snapshots. Launch an iOS application. iOS application goes into the background, takes a snapshot, and you know exactly where to find that snapshot. Might store sensitive information again, and so it's one of those places that people usually check for. Caches. So the application directory is going to have a caches directory, and that caches directory functions almost similar to your web browser's cache, pretty much aimed at improving performance. And again, it may store web cache content and may store sensitive information again. And so it's just a bunch of tables, and you interact with it through the SQLite 3 command line tool again. Dumping binary cookies. Binary cookies created by the URL loading system, stored on the file system in binary format. Of course, the assumption made by the developers is that if it's in binary format, nobody will be able to get to it. Of course, there are tools that allow you to parse that and pretty much read it, right? IPC, inter-process communication. So the application registers a custom URL scheme, and then the application is invoked when the URL scheme gets called. And so usually you would dump the application binary, and then you would probably run strings on the application binary, or you could create a plist, and then you would grep for a particular string, right? And this was abused back in the day. Skype had a bug where you could pretty much invoke Skype through the URL scheme without the user's consent, make premium calls, right? And so the recommendation here, or the tool that I would recommend you using, is LSD Cript, and to use the public or the private URLs option, right? Pretty much gives you the same thing and then some. Problem though is, as we mentioned when we started out, a lot of these bugs are now being closed. And so the URL attack, the URL scheme attack, is pretty much dead in iOS 9, because now they have introduced universal links, right? And so the developer can now specify the paths that will be opened or processed by the application. Communication is done over HTTPS, and also prior to iOS 9, you could enumerate what apps were installed on the device using the can open URL method. That's no longer the case. So just an example of common bugs that you'll find that are now closed. Injection attacks, web views, injecting into web views, file handling routines, XML attacks, and so on. So the point of this is, keep in mind that the issues that you identify with local storage are only valid or only work when the device is unlocked, right? Some other common results that you might find have to do with unsecured APIs, which you would find using Burp Suite, or some hard-coded secrets. But the fact is that with each iteration of iOS, more and more of the common bugs are being closed, right? So pretty much binary protections are now standard, at least in most of the third-party apps that you'll see. And then, if the developer makes good use of the data protection APIs, that's another thing. And we just mentioned that universal links were introduced in iOS 9 that killed the IPC loophole. So, question we have to ask ourselves then is, what happens when the common tools fail? Or what happens when your Google foo doesn't return anything, right? Or there might be custom security protections in place. Or you might want to extend an existing tool. Point is, at this point, we're going to need to change our approach, right? And so, moving towards this new approach, and I put new in quotes because I know that some people will argue that there's nothing new about this, or there's no such thing as new in InfoSec. So I just put this in new, right, in quotes. So you're changing your approach. And it's going to start with a better understanding of iOS internals, right? And so we're going to look at what happens under the hood, get into ARM32.64 just a little bit, and deep dive into Objective-C and Swift, like what happens under the hood from a reverse engineer's perspective. So the first thing we need to do is kind of improve our toolkit. So what does the reverse engineer's toolkit look like? Disassemblers, IDA Pro, Hopper, and we'll go through this now. IDA Pro, it's kind of the de facto tool when it comes to reverse engineering. Chances are if you're buying it individually, you will have to sell a body part or two. It is extremely expensive. But in my opinion, IDA is to reversing what Burp Suite is to web pen testing, right? And it's very, extensive. You can extend it, write your own plugins, scripts. I mean, an entire talk could be given on just IDA alone. And the I think the most recent version, 6.9.5, also supports iOS remote debugging, right? Hopper, scaling down a whole lot more. Just a couple $100. Doesn't support as many architectures as IDA, but it's enough to at least get you going, right? And I think now it just supports on OS X, I think, but don't quote me on that. LLDB. So LLDB replaced GDB. Just an example here. So it's a client-server setup. So you copy the debug server onto your testing device, and then on the client, you simply connect to it, right? So on the mobile device, you run the debug server. It's going to listen on a particular port, connection comes in, launches the application, you're in business. And an example is shown here. Just some tips. So pretty much what would happen is you launch the application, or you would have the application binary. You would have the binary opened in your favorite disassembler, and then you would be interested in setting a breakpoint at a particular offset. So you'd grab that offset, and then you would run the LLDB tool. You would first of all launch the application on the device itself, and then you would connect, and then you would run, for example, image minus list to list the images, grab the slide, the ASLR offset, and then add that slide to the offset that you are interested in setting the breakpoint on. Of course, you don't need to go through all of this. If the application has symbols, you could always set the breakpoint on the symbols. But it's just multiple ways of doing the same thing. JTool. JTool is the new hotness. So usually you would see O-tool being recommended, right? But an O-tool is the Mako binary Swiss Army knife. But JTool offers O-type functionality with a lot more options, right? So you can do Mako analysis, you can run strings, NM, supported on multiple platforms, OS X, iOS, and it's a ARM64 disassembler. And so an example is shown here of dumping the text section of a simple binary using the JTool minus D option. The bonus, though, is that JTool also operates on the shared cache. And for those who may not be familiar, the shared cache is a single file with pre-linked system libraries, gets loaded once, and then is shared by all other processes, right? Using JTool, you can list the libraries that are in the shared cache, one, and if you are interested in, extracting that library to go and do like further research, JTool also facilitates that. And if you're interested in how the shared cache can be abused, I would recommend checking out Pangu's talk at Black Hat earlier this year. ProcEXP, getting task-related info, so you can display threads, map ports, dump core image, and a whole lot more. And then, of course, there's GDB. When I was putting this together, it was not supported on, ARM64 architectures, and so you're left with using LLDB. FileMon, very useful tool. If you want to see how an application interacts with the file system, very useful. And of course, it traces the file system activity using FS events, right? Very useful. And then there is the Apple CC tools. So you have O-tool, which we mentioned earlier on, Mako Swiss binary knife. You have NM for dumping symbols, LiPo for thinning the binary. The binary may be a fat binary, which means that it supports multiple architectures. You might just be interested in a particular architecture, so you use LiPo to thin the binary. And then there's code sign for binary signing. Truth is, you need none of this. JTool pretty much does all of this and then some, right? So we've looked at the common tools, common tests, realized our limitations, realized that we need to change our approach, and so we improved our toolkit. And now we're going to get into the fun part of the talk, which is, reverse engineering iOS applications and what happens under the hood. So We're going to look at we're going to start with the Mako binary format, then move into MacTask. Simply, I'm going to introduce ARM3264 at a very high level, and then look at what happens under the hood with Objective-C and Swift, right? Now, every OS has its own binary format. Windows has PE, Linux has ELF, OS X and iOS have Mako, right? And this is because, at a brief history lesson, at the heart of iOS OS X is the XNU kernel. And at the heart, and XNU, that kernel is, has like 3 major layers. So you have the BSD, IOKit, and Mach-O, right? And so at the heart of XNU kernel is the Mach microkernel. All right, so of course, if you're gonna do any assessments on the binary, the application binary, you need to know where it is, right? So in prior to iOS 8, var mobile applications, and then iOS 8 and beyond, they split it. So now the application binary is at one location, and the data that the binary uses is at another location. And then in iOS 9.3x, I realized that now the app binary is in var containers bundle application bundle ID. Just something to note. So, what is this Mako binary? Quite simply, has a header followed by a number of load commands followed by data, right? The header itself pretty much indicates whether or not the binary is a 32-bit or 64-bit binary. Also indicates the architectures that it supports. The file type also indicates whether or not it is a dynamic library, core file, executable, and so on. And then there are a number of flags. And incidentally, some of these flags are what you would check for during an assessment. So you would usually check to see if the binary was compiled using, ASLR, and so you would check for the PI flag. So using JTool, -H to dump the header, -V to increase for verboseness, if there's such a word. And you dump the headers, right? Now, the binary is going to have a number of instructions. And these instructions are going to be essentially determine how the binary gets mapped into memory, right? And these instructions, some are going to be processed by the kernel, and some are going to be processed by the dynamic linker, right? We refer to these instructions as load commands. Now, one of the most important load commands is LC segment. And a segment is pretty much memory regions that have the same read-write executable protection, right? So as we said, some of these load commands are going to be handled by the kernel, some are going to be handled by the dynamic linker, right? So things that the kernel will handle are like LC encryption info, that deals with encryption. LC code signature, that deals with code signing, and code signing is heavily used on iOS. LC main, the binary's main entry point, right? And so, what are these segments? You would usually see page 0 for null pointer traps, and that segment usually has all its access permissions revoked. So for example, on 64-bit architectures, the entire 32-bit space would be dedicated to this, or the first 4 gigs. And then you have the text segment, which deals with program code, data segment, read-writable program data, link edit, symbols, heavily used by the dynamic linker. And then you have the restrict, and the restrict segment prevents you from force loading your own dynamic libraries using the DYLD insert libraries environment variable option. And then each segment is going to have an optional section. What does this look like? Just an example here. But to dump the segments, you just use JTool -L, list of segments, example is shown here. Or if you prefer to use the GUI option, you could always use the ever popular Mako view tool, right? So after the kernel is done doing what it does, it hands over processing to the dynamic linker. And the linker pretty much is going to resolve, among other things, symbols, and it's going to load each it's going to load each LC load dilate command. So if you go back to the binary, oh, I'm going the wrong way. Right, so if you go back to the binary, you'll see a bunch of LC load dilate at the bottom. The dilinker is going to load those commands, and also the LC load dilinker specifies which dilinker will be used. In this case, /user lib dilate. Also very important, the dynamic linker supports interposing or method switching, and so all you need to do is add the interpose section to the data segment. And you could force load your libraries again using the DOLD insert libraries environment variable. And just to note that code that has the attribute constructor will auto-run. So in your dynamic library, code that has the attribute constructor, once the dynamic library gets loaded, it will auto-run. And so most people might be familiar with dynamic libraries if you use dump decrypted for injecting into a process and dumping the binary itself, because binaries from the App Store are encrypted, and so, but once they get executed and loaded into memory, they are unencrypted. Dump decrypted inserts a dynamic library, reads the binary out, plain text, boom. So what are Mac tasks? So at this point, the binary is loaded into memory, right? And on other systems, you would call this a process. In the world of Mac, this is a task. As with other systems, processes need to talk to each other, and so you have inter-process communication. To facilitate inter-process communication, each task has a port, and a port is simply an IPC endpoint. The point here, and very important point here, is if you are able to own that port, you own that process. And by own, I mean you have full control of that process. So the logical question is, how do you own that port? Two options. You could use the Mactrap task for PID, where you pass in the process ID of the process that you are interested in, get a handle, done. Depending on the jailbreak, if it is patched for task for PID 0, that means that you could read kernel memory, right? The other option is processor set tasks, which will, return any task port in the system. So as we said, owning the task port means you own the process. And so to interact with the task, get the task port. Once you have it, it's pretty much left up to your imagination as to what you want to do. You could read write memory with using the powerful Mac VM APIs. You could inject your own shellcode. Pretty much left up to what you want to do. And an example is shown here. Task for PID grabs the port, and then you pass that handle into, in this example, Mac VM region. Just an example. Dumping memory, you could write your own code again. So you pretty much get the task port, use the Mac VM API's read memory. Or, quite simply, you could use procexp using the regions option, which, so you procexp, process ID, regions options, and then you take the region that you are interested in, pass it to LLDB, dump it, write it to a file, copy the file off the device, and you're good. So, ARM assembly, of course, we're targeting ARM devices here. So very quickly, 32, ARM 32, bunch of registers, R0 to R12, general purpose. We have our stack pointer, we have our link register, which stores the return address after a function call, and we have the R15 being the program counter. What is important, though, is to understand how functions are invoked and how parameters are passed to functions. So R0 to R3, first four function parameters, return value is usually stored in the stack. Functions are invoked using you can branch and exchange, where branch and exchange means you're going between arm and thumb mode. Branch and link, return address is stored in the link register. Branch, link, and exchange, combination of all three. Basic loading instructions, ARM is a load store, and so before you can use data, it must be loaded into the register, right? And how I remember this is loading goes from right to left, storing goes from left to right. That's it. ARM64, a lot more registers. So now you have X0 to X28, general purpose, 64-bit registers, W0 to W30, 32-bit. Of course, you have your usual suspects again, frame pointers and so on. But and again, how arguments get passed to functions and so on. An entire talk could be just done on this section alone, right? So this is just to introduce you to just enough to at least get you started. Objective-C. Prior to iOS.
Hi folks, Iron Geek here. Unfortunately, we had another video problem with the Avid Medias, and you don't have the audio until about the 38-minute mark. But we'll get that back up shortly. Sorry for the inconvenience.
And all this application does is you click on a button, checks to see if a certain file exists. And if it does, prints the device is jailbroken. If not, it's not jailbroken. Cool. That simple function gets translated to this everlasting thing that you're seeing here. Right? So, first thing, _T, Swift symbol. F indicates that it's a function. Then you have the C that indicates it's a function that belongs to a class. Then you have the module name, prefixed with length. You have the class name, prefixed with length. Function name, prefixed with length. This SOFTS, I have no clue what that is. So if somebody is here who knows what that means, please tell me when the talk is done. And then you have F, function attribute, followed by your parameter and your return type. You don't have to do this by hand, though. You could use the Swift demangle tool to assist, or if you're using Hopper, there are plugins that automate this process for you, right? So, we're going to get into jailbreak detection routines, simple jailbreak detection routines, how we can identify them and how we can bypass them. So, we're going to now, try and apply some of the things that we discussed earlier on, and see how we can now bypass simple jailbreak detection routines. So we're going to discuss binary patching. That's the method that we're going to use. Before we proceed, yes, you could do this with several other tools. You could use XCon, TS Protector, Officer. In fact, some of the very tools that we discussed earlier on, Frida, for example, you could use to accomplish some of the things that we're going to discuss now, right? But the question again is, what happens when you can't? And so the idea behind this section is really to introduce you to assembly, right? Like I said, when I started out, I just ran the common tools, didn't care much for the assembly. And so this section is just kind of aimed at introducing you to assembly, right? And the best way to do that, I thought, was to use like some simple examples. So binary patching 101, you can replace an instruction with a not, no operation. You could change conditional instructions to one conditional one, so branch not equal to just a branch. Update the register itself, and going back to that restrict segment, as I said, sometimes you're going to encounter a binary that prevents you from force loading your own dynamic library. Because of the restrict segment, you're going to have to either remove it or patch it out. Jailbreak detection routines. Jailbreaking a device usually results in some artifacts being left behind. The ones that we're going to look at quickly: known file paths, inline functions, checking to see if the sandbox is still intact, and some methods that developers might use to deny debugging. Simple routine here. So we have our isJailbroken function, and it just checks to see whether or not certain files exist. Cydia App Store, SSH. But what does this look like from a reverse engineer's perspective? Simply put, we see the call to our isJailbroken function. Return value gets stored in register W8. We see a comparison against 0 with register W8 and then a branch. So all we need to do to bypass this check is patch that comparison. Done. Like I said, pretty straightforward and simple. Some might say, okay, but this is a contrived example. Nobody does this. Enter in Ticketmaster. You install the app on the device. Pretty much allows you to purchase tickets for a number of events, right? Install on a jailbroken device. Prompts you that, jailbreak is detected. Open it up in a disassembler and you see, again, checks for known file paths, some common file paths. And then reading through, you realize that there's a comparison between register, that there's a move instruction that moves a 1 into register W9. And then W9 is stored and is later used later on in the application to determine the state of, to determine whether or not the device is jailbroken. All you need to do is write a 0 to register W9 and it's done. Inline functions. Basically, change the declaration of the function. Now, instead of seeing a clear branch to our jailbroken function, we're now looking at the body of the function itself. And all this does, it just increases our time that would normally spend reverse engineering, because now you're going to have to read through the entire assembly, right? But again, usually there is some comparison. And so if you could find a comparison and update the register, and again here, we're seeing a comparison of W8 against some value, and based on the result, a particular branch is taken. All we need to do is update this command. Fork. In a properly functioning sandbox, the call to fork should fail. From a reverse engineer's perspective, again, you see the call to fork. Reading through the assembly again, we see a comparison of, what is that? W8 again, and based on the results that are checked, we see a branch. Again, all we need to do is update this particular comparison to take the branch that we want. Pretty straightforward. But to get to this point, it just means that you'd have to not be afraid of the assembly and just read through the instructions, right? Ptraced prevents you from tracing the application, and so there's a syscontrol call. The results is then returned in a struct where the P flag is going to have the status as to whether or not the device is being, as to whether or not the application is being traced. And then we see an AND operation against the P_traced variable, right? But this ptraced variable is defined in sysproc.h as that value. And so if we look in our disassembly, then we again see the AND instruction of W10 against the ptraced value. And so all we need to do is read the register using register read, We see the value there. And so to bypass the check, all we need to do is update it to any arbitrary value. And in this instance, I just wrote a 0, right? So that the AND instruction, that check would fail. And pretty much done. Deny attach, prevents you from attaching to the process. Deny attach, of course, is defined in sys ptrace.h as 31. And so in this instance, again, using JTool, put the actual function and the disassembly. And so we see our call to DL open, we see the call to what is that? DL sim. So basically we kind of have kind of like a one-to-one mapping of what's going on. And then we see an OR operation against W9 with the value of 1F, converting 1F to decimal, 31, PT deny attach value. And so all we need to do is patch that, and you're done. I had a simple application developed in Swift, and so I have in this instance, is jailbroken function that is implemented in C, and in this case, it's just checking to see whether or not certain files exist, similar to what we did before. Calling this from Swift, call a function, check the return value based on the value that's returned, print a particular message. From a disassembler's perspective or reverse engineer's perspective, we again see the mangled names. And in this instance, I'm using JTool, again, to disassemble that particular function. And of course, we see our call to our jailbroken function. Value gets returned in W0. See a comparison of W0 against 1. So all we need to do is patch that comparison, right? So wrapping up, the fact is that the common bugs are getting close, right? Most binaries these days have the binary, from the App Store, have most of the protections that are, pretty much standard. ASLR, stack cookies, that kind of thing. And so, we kind of need to change our approach. And changing that approach involves not being afraid to look at and read and make modifications to assembly code, right? Also, if you want to move into iOS, into looking at the iOS system itself, then you're going to have to, get into reversing and so on. And, disassemblers are really your friends. And I would encourage you to add the reverse engineering skill set to your arsenal. I discussed some simple jailbreak detection routines. But there are some commercial tools that, are custom, and it's not as straightforward as this. And, it's going to require you to get really deep down, go through the assembly code, identify what's happening, and make the patches. So again, main takeaway, add the reverse engineering skill set to your arsenal, opens up a whole new world of testing. And that's pretty much it. Thanks for coming. Appreciate your time. Oh, by the way, so these are the, if you are interested in getting more information on the tools that we discussed, these are the books, blog posts, and so on. If you are interested, for example, in ARM exploitation, in learning more about ARM exploitation, ZipItAsec has a very cool course. If you are interested, again, in iOS, OSX reverse engineering, Jonathan Levin, again, also has a very cool course. So at least those 2 courses will get you started and on the right track. Thanks for coming. Appreciate it.